This lesson is an introduction to state space modeling in R for forecasting. And we're going to be doing this using JAGS and the RJAGS package. So you'll need to have both JAGS and RJAGS installed for everything to work. State space models are a kind of autoregressive time series model, but instead of having an arbitrary number of autoregressive components, so like we've seen before, like a 1 month lag, a 2 month lag, a 1 year lag, these typically only have a single first order autoregressive component, so they just use the information from the previous time step. What's different about state space modeling compared to what we've done so far is that it allows us to incorporate uncertainty in the observation process. And it does this by separately modeling the process model, which captures how the system actually changes over time, and the observation model, which models how observations are made on that underlying process and allows us to incorporate things like observation error or indirect observations. And what's cool about this is that as part of what the model is doing, it estimates the true value of the underlying, what we would call latent state variables, which are often the things that we're most interested in understanding biologically. To explore this today, we're going to use a modified version of an exercise put together by Mike Dietz as part of his forecasting book. And this works on the Google flu trends data. We're coming up on flu season here, so this is an interesting topic to explore. And what Google flu trends tried to do a few years ago was to collect information on people searching for the word flu or symptoms related to the flu as a way of trying to understand how much flu there was going around in different areas. And we'll look at this data for the state of Florida. Let's go ahead and just get set up for doing things. We'll go ahead and load the library that we're going to work with, RJAGS. We'll come back and talk about that in a minute. When you load it, you should see that it's successfully linked to JAGS. If not, you need to make sure that you've installed the JAGS software itself. This package just uses that software, which is separate from R. We'll then go ahead and load in the Google flu trends data for Florida, and we'll call it gflu for short. And we'll assign it the output of read.csv, and now we'll use read.csv to download the data for us directly over the web. And so inside quotes, instead of a file name, we can provide a URL. So we'll type http://www.google.org/flutrends/data/flu with an F /us/data.txt, and then a comma, and there's some metadata at the top of this file, a bunch of rows of text describing what the data is, and so we need to skip that to load the data into R, and so we're going to say skip is equal to 11, and then run. And then if we click on this, we'll see that we've got a table of data. It includes dates starting back in 2003 and running up through 2015. And then there's this index of flu-related search terms for both the United States as a whole and each of the states separately. And since we're going to focus on Florida, our data is in the Florida column of our GFLU data frame. And so let's pull out a couple of pieces of information from this data frame. First, let's pull out our date column, and we'll call that time because we're thinking of these things as time and time series. And we will get that as a date. So we'll say as dot date with a capital D. And then we want the GFLU data frame $, the date column. And then the other piece of information we want is our response variable. We'll be writing this as y when we look at it as equations. So we'll write it as y here. That's typically our observed response variable when we write these things down. And that's going to be the Google Flu index, that number of how much flu that is, how much flu there is, how much searching there is about flu. And we'll get that for Florida, so $ Florida. And so let's go ahead and plot this data just to see what the time series looks like. And so we'll do plot time on the x-axis, our flu index on the y-axis, and then let's make this type is equal to L in quotation marks to make it a line plot, since that's how we often look at time series. And if I make this nice and big here, we can see that we've got this trend in the flu index over time for the last decade or so. And we see the typical seasonal trends where we have very low amounts of flu during the summers, high amounts in the winters. Some years there's not a lot of flu, and other years there are big spikes. And this is what we'll be trying to model using a state space model today. Now, in order to understand what we're about to do in R, we need to talk for a minute about exactly what the structure of these state space models is like. And so the way that these models work is we have two separate models. We have one for the process and one for the observations. And so the basic idea behind these models looks like this. Our process model takes information from the previous time step to predict what's going to happen in the next time step. And so our process model operates something like this. We've got x at time t minus 1, and we use that information to predict x at t, and then we use that information to predict x at time t plus 1. And this is our process model. And so we'll start by using the same kind of autoregressive models we've used in the past to build this process model. Our observation model then comes in to allow us to translate between these latent values that are actually going on in the system and what we observe. And those happen at each time step. And so the idea is, if we have a latent value, a real value of x at t minus 1, then we've got another model here that tells us what we would observe at y at t minus 1. So y at t minus 1 is our observation. And so that model governs the observations at each step. And so we have the same model that gets us from x at t to y at t at each step. And so this then this relationship right here is our observation model. And we'll look at some specific examples of this right now. So let's look at how we might actually do this mathematically. The first is what's actually happening in the system. And so in our case, we're trying to model the actual prevalence of flu in the community, probably something like the total number of people infected with the flu. And we want to model that using some sort of first order autoregressive component as our starting point. So we might have, right, just in the generic sense, we'd say that x at t plus 1, so the amount of flu at the next time step, is equal to some function f of x at the current time step plus some error term, which we'll indicate by epsilon here. And the simplest version of this, the kind of simple AR1 model that we've been using so far, is to say that x at t plus 1 is equal to some constant or mean value plus some coefficient times x at t plus an error term, and that error term that we've used so far is normally distributed error with a mean of 0 and some variance. So that's what we'll use for our starting process model. So then we have our observation model, and an observation model here is clearly important. Google searches for flu symptoms are definitely not perfect measures of the number of flu cases, which is what we're really interested in and what's really changing over time. And so we want to be able to model this imperfect observation. And this probably isn't sufficient, but we'll start with a very simple observation model that says that searches are approximately right, but that there's some error around them. These could be much more complicated, but we're going to start with the simplest case possible. And so we'll say that our observed value, the number of searches for flu and flu-related terms, and we'll write that as y at t, is equal to x at t, which is the actual prevalence of flu in the community, plus some error. And for now, we'll go ahead and again model that error as normally distributed with a mean of 0 and some variance. But again, we might want a much more complicated model where we kind of figure out how these two terms are really related to one another and incorporate that mathematically. And so these kinds of models are really cool because they let us start to build in increasingly complex versions of uncertainty about the world. But as a result, they're not trivial to fit because these errors are all related to one another and interacting as we try to fit the parameters of these models. And so we can't fit them straightforwardly using standard methods. And so we're going to use a Bayesian approach today using a set of software called JAGS, which stands for Just Another Gibbs Sampler. And Gibbs samplers are a way of exploring parameter space to fit the model using Bayesian methods. And so in effect, this sampler is going to explore different possible values for the parameters of our model and find the ones that provide the best fit to the data for us. And to start doing that, we're going to move back to R. Like I mentioned at the beginning, we're going to use the rjags library. And what the rjags library does is it allows us to write JAGS code, which gets run in a separate piece of software to do the actual model fitting. But we store it as a string in R, and then rjags sends it out to JAGS, does all of the fitting, gets the results, and brings them back to R so that we can work with them further there. So the first step is to write our model as this string in R. And we're going to start with the simplest possible model that there is, which is a random walk. So we won't worry about having a mean or a coefficient associated with our x at t minus 1 step. We'll basically just have x at t is equal to x at t minus 1 plus some error. So we'll call this model then random walk. And we'll say equals. And then it's a string, so I'm going to create some quotes and then hit enter a couple of times. And because this is a string, R will keep all of these different lines together, but in a way that we can read this and also JAGS can read it for creating our model. Now there are 3 components to our model. We've already talked about 2 of them. We've got the process model, which relates the state of the system at time t to the state of the system at time t minus 1. We've got our data or error or observation model, which relates our observed data to our latent variable, so that relates y to x, and we're going to use Gaussian observation error. And then there's a third part that we haven't talked about, which are priors. And Bayesian methods need priors or starting points for fitting their models. And we can also, in more complicated situations, use them to really inform the model about what the parameters are based on some external knowledge. But we're not going to do that today. I'm just going to give us a little more space to work here. We're going to first start with the word model. This is our way of telling JAGS that we're starting a model. And then curly brackets. And then hit enter. And I'm going to tab over to indent things. And then we'll put a comment here to label this section of the code. So I'll add a few comment symbols and then we'll say observation model. And our observation model is just normally distributed error around x. And so in R, we might normally be able to write a formula like this. Y is related to, that's the tilde symbol, dnorm, that's the normal distribution of x with some error. And just to make things a little extra confusing, instead of using variance, JAGS uses precision, which is 1 over the variance. And so we're going to actually call this tau, because that's what we would normally use to refer to precision, underscore obs for observation model. And we'd like to be able to write things like this. This is how we would normally write them in R. But in JAGS, we have to loop over the values in our time series and in effect declare this or use this model for each value separately. And so the way that we do that is just like we would write a for loop in R. And so we say for parentheses t for time in 1 through n. so 1 through the number of observations, curly brackets. And now I'm going to go ahead and move our model up into this for loop. And now we need to tell it to do this for each value in x and y incrementally. And so I'm going to type some square brackets here to say use the t value from y, the tth value, and the same for x. And so this is Jags's way of saying we've got a model, and the value for y at some time step t is the value for x at that time step t, and it's drawn from a normal distribution with that as the mean and tau obs as the precision. And the reason that it shows up this way is because there's another way of writing this last line in our model. So far, we've written it as x at t plus some error, but this is exactly the same as writing this as a normal distribution with a mean of x of t and the same observation variance. Okay. So instead of having x at t plus a normal distribution with a mean of 0, we can write that exact same thing as a normal distribution with a mean of x at t and the same variance. So that's our observation model. Now we want to do the same basic thing for our process model. So we'll go ahead and label that here, process model. And now we know we need to do this looping. And so we'll say for parentheses t in, and now we're going to say 2 through n. And the reason for that is that our model predicts the current time step based on the previous time step. And so we can't actually make a prediction for the first time step. We have to be able to go back one further. If you're thinking about these things as being vectors in R, to predict x at time 1, x at that first position, we would have to look at x in position 0, and that doesn't exist. And so we'll start with 2 and 1, so we fit within that vector. We've got our curly brackets. And now we'll say that x, because this is our latent variable, this is our actual amount of flu, square brackets, at time t, is related to, and now again, we'll write this in this new probability notation. So we'll say d norm of x at t minus 1, right? So the previous time step is influencing the current time step. And now we have a new variance, which is the variance associated with our process model. And again, we're writing it as a precision, so we'll say tau underscore PROC for process. So these are the two things we've talked about so far. And then the last thing we need are priors. And we need priors for anything that doesn't get predicted by the model, any starting point that the model needs to make its first prediction. And so that includes a couple of things. First, we need a prior for our initial observation, for our initial conditions. And so for that's for x at the first time step, so x at 1. And these all have to be probability distributions. They can't just be fixed values. And so this is we're going to say that this is normally distributed, d norm, around x underscore IC. So that's going to be the initial condition for x. And that's going to be something that we pass the model when we get started. And then there will be some variance associated with that as well. The second thing we need a prior for is our observation variance, because this isn't being produced anywhere in the model. It's not coming out over here. And so we need a prior on tau obs. And we're going to set that to a gamma distribution. And we're doing that because this is a precision. So because these are 1 over the variance. And people smarter than me have figured out that good priors for that are gamma distributed. And the gamma distribution takes 2 parameters, A, and so we'll say A underscore obs for observation, and R. And we'll say R underscore observation. And so then the last thing left in here, we get all of our Y's from our X's. We get all of our X's except the first one from X at t minus 1. We've got priors on the first one and our tau observation. And so the one thing we have left that we need to put a prior on is our tau, or precision, for the process model. And our tau process prior is going to be the same structure as the one for tau obs, because it's still a precision. So we're still going to use d gamma to give us a gamma distributed value, and that's going to take A, but now underscore proc, because we're having separate priors for the process and the observations, and then R underscore proc. And so that's our full model for JAGs. We've got the observation model that says for each value of t, for time, we can get the observed value from the underlying latent state, normally distributed with some error. For the latent state, we can get the current value from the previous time step as normally distributed around that value plus some error. And then the priors are a normal distribution around the initial condition, around that starting latent value, and then gamma priors on our precisions, on our variance measures. And that's the model that we're going to pass to JAGs. In addition to that model, we also have to pass JAGs information on the data that it's going to be fitting to and any other information that it needs. And we're going to do that by creating a data object. And we pass it a named list with the information that it needs. And so we use the list function. And I'm just going to go ahead and start a list here. And so we'll have y, which is equal to ry. JAGs also needs to know how long the data is. It uses this how long is the data value up here, n. And so we can say n is equal to the length of y. And then we need to pass it the information that's used in here for generating the priors. And so we need to pass it an initial condition for x. And we can look down here and sort of get a rough idea of maybe how many flu cases there are. And we'll just kind of take a rough eyeball estimate of the average of about 1,000. The priors are going to be relatively weak and uninformed, so we just need a reasonable starting point for the model to fit things from. And so then we can set tau for that initial condition, the variance, the precision there, equal to 1 is a reasonable starting point for precision. We can certainly do more complicated things, but we'll keep it simple today. And then we'll also use 1 for all of our starting parameters. And so we'll say aobs is equal to 1, robs, I should actually type the 1, is equal to 1, aproc is equal to 1, and rproc is equal to 1. And there are, again, better ways of calculating these, and so if you're going to do this for some real research, you should just spend some time Googling sort of how to set these starting values for your priors. And so we'll go ahead and create that named list here. And then there's only one more thing that we need to create in R that JAGS needs before we can start actually running these models. And that's the starting points for our parameters tau proc and tau observed. So we have 2 real parameters in our model, and we need to provide starting points for the Gibbs sampler to search from. We'll store those in a variable called init, and just to make things nice and complicated, we need to provide it with a list that contains a list. And so we're going to have one call to the list function, and then inside it, another call to the list function. And in here, we're going to provide a named list with starting points for those parameter values. And so the first value that we're going to provide it is tau proc. And remember that tau proc is our variance associated with our process model. And so it's the variance associated with the change between x at t and x at t plus 1. And so to estimate that, we're going to take the variance of the difference of y. And so this is basically going to take the difference between 2 neighboring values and look at the variance associated with that, which should be a rough estimate of what that variance looks like. But remember that this is a precision, so it's 1 over the variance. So then we're going to write this as 1 over the variance of the difference of y. And the idea is that's just a good starting point for this calculation. And then we're also going to estimate tau obs. What's our best starting point for that? And here, because this is the variance relating x and y, we don't have quite such an obvious way to choose it, but we'll base it roughly on the variance of y as a starting point. And so we could write this as 1 over the variance of y. I'm going to actually make the precision a little higher. Clearly our error isn't the full amount of ups and downs in this time series. That's got the autoregressive component in there as well. And so we'll actually put a 5 up here, which will make this more precise, which is less variable as our starting point. So now, finally, after all of that setup, we can actually send this model off to JAGS and start to look at what comes back. Let's give ourselves some space here. So I'm going to go ahead and call this J_model for JAGS model. And I'm going to set this equal to JAGS.model. So this is where we're going to declare our model to JAGS. We need to give JAGS our model. That would often be done in a file because, as you can see, these strings get kind of long. So to put that file in, we'll say file, but now we're going to use the text connection function with a capital C, and then the name of our model, which is random walk. And so this is going to treat this string like it's a file that contains that string and load it into this file variable. We then need our data and our initialization, both of which we created. And so we'll say data is equal to our data object, and inits with an S is equal to, and we called this one init without an S, init. And then we need to specify something called n.chains. And that's the number of different searches for parameters that JAGS is going to run. We're going to use one to keep things quick for an example, but typically we would want to run multiple chains just to make sure that this iterative fitting algorithm doesn't get stuck in the wrong part of parameter space, something called a local optimum, and not find the actual results that we want. So let's go ahead and run that line of code. And we can see that what comes out is that JAGS has compiled a model graph. So it's basically said, I've looked through your text description of a model and I've built the version of it that I know how to do things with, and everything looks good. And it's got some information about how it's done that, which we're not going to get into what's going on here. And then it tells us that it's initialized. And so what that means is it's created a model object, but it hasn't actually done anything with it yet. The way that we get JAGS to actually do something to run the model forward is using the coda.samples function. And so we're going to run coda.samples, and we'll store the output in JAGS underscore out, and we'll set this equal to coda.samples. And coda.samples is going to take a model name. So model is equal to, and that's our J underscore model here. It's going to take the variable names that we want it to give us back information on. And so for now, we're going to say variable.names is equal to, and we're just going to ask it to give us the parameters for the moment. And so that's our two precisions that capture the error terms in those normal distributions. And we're going to start with those because they're going to help us figure out whether the model's actually been fit, whether the algorithm has found the right parameters yet. And so we'll give it a vector with strings for the variable names. And so the first one that we want is tau for the process model, and the second one is tau for the observation model. And then the third thing that it needs is the number of iterations, or the number of steps in this search process where it looks around in possible parameter space to find the parameters. And what we're actually going to do for this first step is set n.iter, the number of iterations, equal to 10,000. And we're actually going to run this now, not to give us the answer, but to run through a number of iterations called the burn-in. And the idea behind why we need burn-in is based on the fact that we've given our model starting points, And then it has to get to the point where it finds the real values. So we have two parameters in our models right now. Right? We have tau for our process model, and we have tau for our observation model, right? And so we gave it some starting point, say here, that was a single starting point value for tau obs and tau proc. And now we want it to go find the real values. But generally speaking, our first guess is going to be wrong. It's going to be outside of the reasonable range. And so we'll see the early steps in the model fitting process move kind of directionally. And so it'll guess there and guess here. And we'll see kind of a random walk for a while towards the real value. And then once we get to the real value, the steps in this search will tend to center around that value. And this area right here is where we really want to get our information from. And so we want to be able to throw away this period here, which we call the burn-in. And so we're going to run this model for a bit that will hopefully take up that burn-in, and we'll look at to see how we can tell that. And then we'll run it some more to actually see this portion down here, which is the stuff that we want to really be able to understand. All right, so let's go ahead and run this burn-in step. And we'll see it gradually progress. It'll have a progress bar. With more complicated models, it can take a long time to run iterations. And so it's going to tell us sort of how well it's doing. And so then we can go ahead and plot these samples, get some information on these samples by plotting this jags.out object. And if we do this, we'll see a couple of different things. The first are the trace plots. And this is how we tell whether or not we've managed to go through the burn-in. The easiest place to see this here is here for tau obs. You can see that this is our starting point guess down here at the bottom. We were well outside of this distribution. It takes a few steps, and then it gets up here into this sort of fuzzy caterpillar phase. And that's generally what we want to see for things having converged, having gotten into that key box where we want to take values from. We can see the same thing over here for tau proc. We were way too high on the precision, and after a few time steps, it managed to get itself down here into the fuzzy caterpillar phase. And then these are just frequency distributions of the values from across this entire time series or iterative series from the trace plot. So we probably didn't need 10,000 steps to burn in. With more complicated models, we would need something more like that. And so now that the burn-in is complete, we want to go ahead and run another round of samples. In fact, I'm going to copy this burn-in code and put it down here again. And now, in addition to wanting our parameters, we also want to get out information on the latent variable, the X value, the actual prevalence of flu in the system. And to our variable names, then I'm going to add X at the front. Let me move these down so we can see everything. And the way that JAGS works is when we run this after having run this before, it's going to start where it left off. And so this will run things, it'll return X, but it will start after all of that burning in had been done. And so we'll get just these good samples once the model has found the right general area of parameter space. And we'll run this for another 10,000 iterations. And so now we want to visualize the model's estimates of our latent variable X through time. We need to get out just the piece of data that we want, which is those X values. And to do that, we need to start by converting our output into a matrix and then dropping the parameters from that matrix. And so we'll call this output is equal to as.matrix of jags underscore out. And then if we look at output, what we'll see is we have the precision estimate for the observations, the precision estimate for the process model, and there are 10,000 of these, so these are one estimate for each sample, for each step in this Markov chain Monte Carlo process. And then also for each step, we have estimates for X at the first time step, X at the second time step, X at the third time step, and so on, all the way out to X at the 48th time step. And that's not actually all of them. That's just the ones that our studio is displaying. We've actually got 622 columns, so we've got 600 estimates, which is about right for the length of this time series. And so now let's just get the X values out. And so our X's are equal to our output. We want all of the rows, so we don't put anything at the start of the square brackets, but then a comma, and then we want just the columns starting at 3, so 3, colon, through the total number of columns. This is going to be ncol for number of columns, and then of the output. And so now if we look at X's, we just have these 10,000 samples for each of our 620 time steps in our model. Our point estimates then are the averages across all of these different samples. And then our uncertainty will come from the variance among those samples. So let's start with the point estimates. We can do that by creating a variable we'll call predictions. And we can get the average within each column using the function call means with a capital M. Predictions. And so now we've just got a vector of predictions, which are the averages for each time step. And we can plot those with time. So plot time on the X, predictions on the Y, and we'll plot it as type is equal to line. And so what this is what our model has inferred are the values for the underlying latent state for X at each time step. We can also add information on the uncertainty in these predicted values for the latent variable by finding the range of values that contain 95% of those MC samples. So just like we took the mean for our point estimate, we can now take the range of values containing most of those samples to indicate the equivalent of our prediction interval. And we can do that using the quantile function and applying it across all of our columns. So we'll call this pred interval for prediction interval. And we need to calculate this for every single column, for every different x at time 1, at time 2, all the way up through the end of the time series. And so we can do that using the apply function. We want to apply the quantile function to our x data. So our data is x's. We want to do it column by column. So the second argument is 2. That's the dimension. It says to do this calculation once for each column. And then we want to calculate the quantiles. So the function is quantile. And then we have a vector here, and we want to calculate 2 quantiles. We want to calculate the 0.025 quantile. So that's the value below which 2.5% of the data falls. And so above it is 97.5% of the data. And then we want the 0.975 quantile. And so above that quantile, 2.5% of the data falls. And so between those 2 quantiles, we'll have 95% of our data. And so this is a 95% prediction interval. And we can add this to our graph using lines. We still have time on the x-axis. We now want our prediction interval. And first we'll plot the lower prediction interval. If we look at our pred interval object, we'll see we've got 2 rows, one of which holds that 2.5% quantile, one of which holds the 97.5% quantile. So we want to plot the first row and then the second row. So to plot the first row and all columns, we'll write 1 for the row, comma, and then nothing afterwards in the square brackets, because that'll give us all of the columns. And then we will write this as line type LTY is equal to dashed, and color is equal to blue so that we can see it well. And then we'll add the exact same line again. I'm just going to copy and paste, but now we're going to do it for the second row, and so we have 2 here instead. And what we'll see here is that these prediction intervals are actually very close to the original value. They're a little bit blurry here because of the way we made it, but we can see that there's a narrow range around that predicted line for that latent variable. So the model is really confident in its predictions for x, this underlying state. But it's important to keep in mind that when the model is fitting the values of x at time t, that it has access to the values of y at time t. And so y isn't actually being fit in these contexts because it's already been given. It's actually being used to estimate the error. And so that mean prediction, that point estimate, should be really accurate for x. So then the question becomes, how well will this model actually forecast? Now, to make forecasts using JAGS, we include data for y that is NA, or null. And this tells the model that we don't know those values for y, and therefore the model estimates them as part of the fitting process. So to make a true forecast, we would add 1 NA to the end of our Y data for each time step into the future that we wanted to forecast. In order to hindcast or backcast, like we talked about last time, we replace the values for Y for the end of the time series, the part that we're using as the test data set. And we replace those with NA. And so that's what we'll do today. We'll hindcast. So I'm actually going to go up here in the code to right after we created the data object that we hand to Jags. And I'm going to add a new line that replaces the last year of the time series, the last 52 weeks, because this is weekly data, with NA. And so to do that, Y is inside of this data list. So we'll say data $Y. And then square brackets to indicate the range of values in Y. And so that's going to be the length of Y minus, let me put this all in parentheses. So the length of Y minus 51. So that'll go back to 52 time steps before the end, colon, length of Y. And so from 52 time steps to the end, back to the end, and we're going to set those all equal to NA. And now we can go ahead and rerun our model. So we'll go ahead and recreate the initialization. We'll create our model again. We'll run the first 10,000 samples to burn in. We can then check to see if things have burned in successfully, and it looks like they have. We have fuzzy caterpillars. We can then collect the fitted data that we actually want. Though in this case, we don't actually want the values of X out, because those are the latent state. Let's get out the value of Y, because Y now is the actual observed value, and that's what we want to compare our forecast to, is our observations. So we're going to get out Y instead. We'll still extract it as a matrix. I'll just leave it called X's here so we don't have to change anything below. We can calculate those point estimates and plot them, and now here's our point forecast. And we can already see that probably things aren't going very well because now our point forecast is flat pretty much over this last 52 months. And so not having that observed data to help move things around, the model thinks that X's probably don't change much, and as a result, when we look at our predicted values for Y, they don't change much either. And at this point, we can then check to see how this looks compared to our data. I think we already have a pretty good idea it's not great, but we can do that by adding our observed data on top of this using points. And then we'll have time on the x-axis, y on the y-axis, and then we'll see what that looks like. And we can see what we kind of already knew, which is that our point estimates are now really terrible. We've had this nice up and down dynamic. The model can fit the empirical data really well, but as soon as it's asked to make a prediction with no observed data to help it out, it basically says not much happens, and therefore we miss the point estimates pretty badly. So then the question becomes, does the model know that it doesn't know very much in this forecast area. And so does the prediction interval get wider out there than those fairly narrow prediction intervals than we saw within the training data? So let's go ahead and look. We can rerun these last 3 lines of our code. And here we do get a bit of good news, which is that the model knows that it's very uncertain. And so we see that while it's confident for that first time step, it very quickly realizes it doesn't know what's going on, and the confidence intervals quickly shoot down to almost 0 and almost up towards the sort of most the highest levels of flu that have been seen in the data previously. So it knows it's uncertain, and that's because that error is propagating time step to time step. So it knows that the error in the first time step is small, but the error in the second time step could be twice that big, and it can grow fairly quickly. So that's the forecast, and it's not overly encouraging, but we'll see in a future lesson that we can start to add more to this and hopefully get better results out. Remember that one of the important components of state space modeling is the ability to partition uncertainty among different components of the model. And so we can have this kind of uncertainty in the process model, but separate out the uncertainty that comes in the observation model. And we can look at this by looking at the standard deviations that are estimated for both the observation model and the process model separately. So we've got precisions, which are 1 over the variances. And so if we want to look at this as a standard deviation, which is easier for us to interpret, we'll create a histogram of all of those MC samples of 1 over the square root. So the 1 will get us back to variance, and the square root here will get us to standard deviations. And then we're taking the output from all of the rows and the first column, because that's where our observation precision was stored. And so here we can see we've got a histogram with a standard deviation of a little bit of over 70 on average. And then we can make the same plot, hist of 1 over the square root of output in the second column, if I could hit the keys on my keyboard correctly. And so here's the estimate of the standard deviation associated with the process model. And so we can see actually that the process model variance is up here around 270. And so it's much larger. We have these big random walk steps that represent the changes in the actual process that let us have these big seasonal shifts in the underlying latent state of the flu. And then we have relatively small amounts of variance that actually describe the amount of variability between the observation and the underlying latent state. And so we have this information out separately, and we can look at these values and then interpret them to understand the most important sources of uncertainty for governing our predictions. And if we want, we can also plot those against one another. So we could plot 1 over the square root of output at 1 against 1 over the square root of output at 2. Looks like I lost a parentheses, several parentheses maybe somewhere. And we can see that these estimates are actually relatively independent of one another. They're orthogonal, and so the model has managed to sort of tease apart these two different sources of uncertainty and estimate them independently of one another. So that's the basic idea behind state space modeling and how we use it for forecasting. This approach allows us to separately model a process model governing the underlying dynamics of the latent state of the system and an observation model that governs how observation errors influence our ability to understand the system. It can estimate those separately from one another so we can look at those values and understand what's going on in the modeling. And to make forecasts for these kinds of Bayesian-based models, we then place NAs for the predicted variable, for the Y variable, where we want to make forecasts for, and then the forecasts will automatically be generated as part of the model fitting process. Say x of t is equal to x at t minus 1. Don't worry. I'll try to work on my handwriting when I'm actually doing this. And so we can look at this, and we don't have... the data, we can check. And I've been recording for a while now, and I'm kind of tired, so I'm going to take a break. And then we'll actually run things in JAGS. Maybe I'm going to listen to a little music.